All right, everybody, and welcome to Investigation 8. And this investigation, as well as the following several investigations, talk about large-scale weather patterns, and particularly wind. And this investigation is going to cover the different forces that act on the wind. And so the goals for this lab are first to break wind down into its individual forces and determine how those forces affect the wind. So let's do it. So first off, what is wind? If I were to run into you in the street and just ask you randomly, hey, what is wind? What would you say? Well, what I would say, and a good definition, is that wind is air in motion. And as such, it's subject to Newton's laws of motion. And there are 3 of these laws. We're not going to really worry about the third one, but the first 2 are really crucial. The first one is what's called the law of inertia. And the law of inertia simply states that an object that's at rest stays at rest, or an object in motion stays in motion, unless acted upon by a net force. What this means is that if there's no net force acting on something, it's just going to keep doing what it's doing. Now, we don't usually see this a lot here on Earth because there's so many different forces that are at play. Let's say you're at a baseball game and the pitcher throws the ball. Eventually, that ball is going to stop. Even if a catcher didn't catch it, or even if it just kept traveling, gravity would be pulling it towards the ground. Air resistance from the air would cause it to slow down. There are many different things that would make it slow down. However, again, if an object's at rest, it would stay at rest. If an object is in motion, it would stay in motion unless there's some net force acting on it. Now, with that said, this net force can actually be a sum of individual components. So there may be many different forces acting on something. So for example, with the baseball, I mentioned the drag from the wind, or the drag from the air slowing the ball down. You can have things like gravity pulling the ball down. If the ball is rolling, the friction from the ground is going to slow it down. And all of these individual things add up to a net force. And that net force is this sigma F over here. So sigma just means sum, F means force. And according to Newton's second law, the net force on an object is equal to the object's mass times its acceleration. Now, what does that mean? Well, if we were to assume, and then the third law real quick, every action has an equal but opposite reaction. That's how thrust works. Let's go back to the second law now. If we were to assume that the atmosphere's mass stays even, that it stays constant, that it doesn't change, then that actually means that the net force is only affecting acceleration. And so forces act to accelerate the wind. And saying that the mass stays the same, that's what's called conservation of mass. I'm not going to talk a whole lot about that here. Just the idea is that we're not going to worry about mass. We're only going to worry about acceleration. And so forces act to accelerate the wind. And when I say accelerate, what that means is that means to speed the wind in a certain direction. Either ahead, that's speeding the wind up, behind, that's slowing the wind down, or turning the wind. So basically, forces act to accelerate the wind. Now, with that said, when talking about winds on the surface of the Earth, and in the next activity we'll talk about upper level winds, but near the surface of the Earth, there are 3 key forces that act on the wind. And the 3 forces are called the pressure gradient force, and that's caused by differences in pressure. So all that high pressure, low pressure stuff we've talked about before, that is all important because the pressure gradient force actually is what kicks off wind. Now, once wind begins to accelerate, the Coriolis force then begins to turn the wind. And it turns it in a very set direction. Here in the northern hemisphere, it turns it to the right of its path. In the southern hemisphere, to the left of its path. And I'll talk about that more in a few moments. And then finally, friction, really only important in the lowest 1,000 meters of the atmosphere. But what it does is it slows the wind down. So pressure gradient force moves the wind from high to low. Coriolis force changes the wind's direction. Friction slows the wind down. Now let's talk about each one of these just in a little bit more detail. So let's look at this very simple weather map. These black lines, these are isobars. And I'm sure you remember those from that infamous Lab 1A. Isobars are lines of constant pressure. And they're useful to help identify a predominant pressure pattern. And in this case, we have a point A, which happens to be on the 1,004 millibar isobar. Above it is the 1,000 millibar isobar, and below it is the 1,008 millibar isobar. Because I don't feel like I'm holding any surprises here, I'll just tell you that as you're traveling up, let me go back real quick. As you're traveling up on this map, as you're traveling up, pressure is decreasing, whereas if you're traveling down, pressure is increasing. Now think about this. Let's suppose that there was air at point A. What direction would the pressure gradient force move that air? Well, as we've already mentioned, the pressure gradient force is simply the force that moves the wind from high to low. So high pressure's down here and low pressure's up here. This force, or this point, would be pushed further up. It would be pushed towards low pressure. So the idea here, we have low pressure up here and high pressure down here. And the pressure gradient force is moving the wind from high to low. Now with that said, as the wind begins to accelerate, which is what the pressure gradient force is doing, it's accelerating the wind, it's going to then begin to feel another force acting on it. And that next force is what is called the Coriolis Force. And the Coriolis Force is caused due to Earth's rotation. So it's because we are living on a big globe that is rotating. And what this does is because the Earth is rotating, that actually causes the wind's path to move relative to the surface of the Earth. That actually deflects the wind. And what I really want you to know is that the Coriolis force turns the wind to the right of its path in the northern hemisphere, to the left of its path in the southern hemisphere. And actually the textbook has a really good demonstration on how this works, and there's actually a video demo that I'll include in the comments as well as on this assignment. I didn't do it, so I can't take credit for it, but it works really well. And basically the idea is that if you are moving in a straight path, but what's beneath you is rotating, that's going to curve your path. And that's exactly what the Coriolis force does. And again, the way that it works is it turns you to the right in the northern hemisphere and to the left in the southern hemisphere. Now, one other important thing about the Coriolis force that I haven't mentioned yet is that the Coriolis force is proportional to the speed of the wind, meaning the faster the wind, the stronger the Coriolis force. The slower the wind, the weaker the Coriolis force. In the upper atmosphere, the pressure gradient force and the Coriolis force are the only two things that matter. And what actually happens is, as the wind is accelerating due to the pressure gradient force, the Coriolis force is also intensifying. Eventually, an interesting situation happens called geostrophic balance. So, geostrophic means earth turning, and then balance is obviously balance. This is a balance between the pressure gradient force and the Coriolis force. So here's what happens. So this is a little bit more complicated than the map that I showed you a few moments ago, but really the same idea is here. So we have high pressure down here to the south. Well, yeah, actually, let me put a nice little north sign right here, in for north. There we go. Got our north sign. And we have low pressure on the top of the map, on the north of the map. And then we have our particle. And our particle, let me actually pull up my laser pointer. Our particle is right here. Now, if the particle is at rest and it's released from at rest, there is no Coriolis force acting on it. And the reason why is because it's not moving. The Coriolis force is determined by the speed of the wind. The pressure gradient force, however, is not. It is determined solely by the difference in distance between this high and low pressure. If you remember from an earlier lab, when these isobar lines are very close together, that's a stronger wind. When they're further apart, that's a weaker wind. Well, here's what happens. Suppose I let go of this parcel of air. Well, because of the pressure gradient force and because there is this striving for equilibrium in the natural system, the particle of air will begin to accelerate towards lower pressure. Again, that's the pressure gradient force. And as it's accelerating, its speed is increasing. And as its speed is increasing, it is going to begin to feel a deflection to the right caused by the Coriolis force. So as the particle of air is accelerating, it's going to actually begin to turn to the right. Now, as it turns to the right, the direction of the pressure gradient force does not change. But because the Coriolis force is acting on the wind, that causes the particle of air to turn to the right. Well, eventually what's going to happen is, as the particle continues to speed up faster and faster and faster, the Coriolis force is going to get stronger and stronger and stronger. Now, what will eventually happen is, as the wind continues to turn to the right, it will eventually reach a situation where the pressure gradient force is tugging it in one direction, and the Coriolis force is tugging it in the exact opposite direction. And the two cancel each other out. That's the idea of geostrophic balance. The pressure gradient force and the Coriolis force have now canceled each other out. Now, Terrence, why is the wind still going, though? Why is this air particle still going? Well, I'm glad you asked. Remember, the law of inertia states that an object in motion stays in motion unless it's acted upon by a net force. Between points A and C, there was a net force acting on the particle, which caused it to continue to accelerate. However, once the particle reached point C, the forces were now blowing in the opposite direction. They were pulling the particle in the opposite direction, and therefore they canceled each other out. The net force is now zero, and the particle will just continue in its current motion unimpeded. It'll just continue in its current motion. The only thing that's going to change the speed of the particle is if the pressure gradient force weakens or strengthens, or if the particle is near the surface of the Earth. Now what happens is, here at point D, this actually demonstrates a particle near the surface of the Earth. And, excuse me, and the way that a particle near the surface of the Earth works is, you've got the pressure gradient force pulling the wind towards low pressure, You've got the Coriolis force pulling the wind to its right, but you also have friction pulling back on the wind. And what this actually does is this causes the wind to slow down. And the slowing down of the wind weakens the Coriolis force, making the pressure gradient force the strongest of the three. That causes the wind to then begin to turn back towards that low pressure. And it actually turns back at an angle of 30 degrees relative to the nearest isobars. Okay, now with that said, let's actually break the wind up into these three components. So let's actually take a station model, and let's actually break the wind up into these three individual components. And this is the last thing that you'll need to do for this lab. So here's how it works. So the black line I'm going to draw represents the net wind. The red line will represent the pressure gradient force, the blue line, the Coriolis force, and the brown line, friction. All right, so let's do it. First off, you're going to be asked on this model or on this assignment to draw the direction the wind is headed towards. Now remember though, these station models only tell you about where the wind has come from. They don't tell you where it's going. They only tell you where it's come from. Now here's the good news. The good news is where it's going is just the opposite direction. So in this case, the wind was coming from the west-southwest, and therefore, since it was coming from the west-southwest, it is blowing in the net direction to the east-northeast, like so. And so, I'm drawing my black arrow, indicating that the wind is going to the east-northeast. And forgive the terrible chicken scratch there. But yeah, it's going to the east-northeast. Now let's actually split the wind up into its individual components. The first one we need to look at is the pressure gradient force, which is in red. And the way that the pressure gradient force works is you identify the nearest isobar to the station. So we have the station here. The nearest isobar is right here. And what you're going to do is you're going to draw a red line that is exactly perpendicular to the isobar, pointing at low pressure. So it's going to look something like that. It's going to look something like that. And I think that actually looks pretty good. The next one that you're going to draw, and so that indicates what direction the pressure gradient force is pulling the wind towards. The next force you're going to draw is the Coriolis force. And that I will do in blue to honor this color here. And the Coriolis force will be 90 degrees to the right of the wind's path. So since the wind was blowing this way, and I actually messed up my arrow a little bit, the Coriolis force is going to be 90 degrees to the right of that path. So there's my Coriolis force wind. Okay, there's my Coriolis force wind. And actually that looks terrible because it's overlapping, so maybe I'll just draw it like that. But there's my Coriolis force wind. And then finally, the last wind that they want you to draw is friction. And friction's pretty simple. It's literally just in the opposite direction that the wind is blowing towards. So if you want a nice little trick, see where the wind barb is pointing? That's where friction would be pointing. So let me pull up my highlighter again. And so friction would be going that way. And that splits the wind up into the individual components. So again, pressure gradient, that's going to be perpendicular to the nearest isobar and pointing towards low pressure. Coriolis to the right of the net direction, not the pressure gradient direction, to the right of the net direction that the wind is traveling in, and then friction directly behind where the wind is blowing. And that's really all that you need to know for the slab. As always, if you have questions, comments, concerns, please feel free to email me, and I will include the link to that demonstration video. And that's it. Best luck on this lab. It is one of the tougher labs of the course, but you've got this, all right? Just let me know if you need any help.